We'll introduce the idea of estimation with a very intuitive example. And in this case, we're looking at a coin toss, and we're tossing one particular coin which we don't know to be a fair coin a priori. So we have a coin, we don't know if it comes up heads 50% of the time, or if maybe it's a little bit weighted and that actual percentage is a little bit off of 50%. And that's what we're going to explore with this graph. So the statistic that we're tracking here is the proportion of all flips that have outcome heads. Since that's a proportion and we're tracking just the statistic, which estimates the population proportion, we'll call it p hat, we would calculate this by taking the number of heads and dividing it by the number of flips. The parameter that estimates we would call P, a population proportion. And if we imagine that for this particular coin, we have flipped it 100 times and tracked this sample proportion, what that's representative of is all flips of this coin. So we're interested in the proportion that would come out heads for this particular coin over the hypothetical population of all flips. A much simpler way of saying that is the probability of getting a head from this coin. So some population proportions are probabilities, particularly when the population itself is hypothetical. So here's what we're going to do. First, look at just the first 20 flips. So on the first 20 flips of this coin, we're going to pretend that we cannot see the rest of this graph. So everything after 20 we will not let ourselves look at. And just based on this rather volatile graph that we see up to the first 20 flips, we're going to estimate what we think the probability of flipping ahead could be between. We don't know very well, but we do know that it's not 0, and we do know that it's not 1 because we do see some other values showing up here. What we can see in this graph is that at one flip, our sample proportion is 0, which means that our first flip was a tail. Our second flip must have been a head, since that brought us up to 0.5, so that out of 2 flips we got 1 head. And then it starts jumping around a little bit. We can see that we have a low point and a high point, and that it looks reasonable that the probability of flipping ahead is probably between these two values, though we may add a little bit of a buffer just to be more confident. So doing that, I'll just be very rough here and say between 0.2 and 0.7 for those bounds based on the first 20 flips. Now as we go out to 100 flips, we get to look at the whole graph. And now what we see is, it seems like as it starts to stabilize, the highest value we see is perhaps somewhere around 0.55, and the lowest value we see here is somewhere around 0.45. I now feel pretty confident that the probability of flipping ahead is between these two values. So I'm going to put these as my bounds. But certainly there isn't just one right answer for this, and we are doing this based on intuition. We're not doing any formal calculations for this. Just based on the graph, what can we see? There are a couple of things that this helps us to illustrate. One of them is that as we get more data, we get more precision. So this second estimate showed us more precision than the first one. And that is true for all of the confidence intervals that we're going to look at. So we get a narrower estimate. Another thing that it shows us is that even though we may never know this population proportion, we still can tell something about it based on a sample statistic. We can, by introducing a little bit of uncertainty, give a range of values that we feel reasonably confident that population parameter is between. Now this is a confidence interval, the one that we came up with, or the two that we came up with, both of these are confidence intervals, the two that we came up with aren't very rigorous, and they didn't involve computations really, and it would be difficult for us to give a mathematical level of confidence behind them, but they are confidence intervals. And the range of values is based on the idea of a margin of error. So for example, one way that this comes up often is in our Gallup polls. Gallup polls generally are done with a 3% margin of error, and that margin of error is sort of a give or take this much. So what this means is that if the poll shows an approval rating of 37%, then we believe that the actual approval rating in the whole population, which in this case is probably registered voters or perhaps all adults in the US, is 37%, give or take 3%. So because that 30% or that 37% just represents those who were polled and not the whole population, we would say that it is a statistic. This is our value p hat, which we'll call 0.37. And the exact approval rating is believed to be between the two values you'd get by saying, well, give or take 3%. In one case, you'd subtract 3%. In the other case, you would add 3% to get bounds. So we would say that the exact approval rating in the whole population, so this is P, is between 34% and 40%. So another way of talking about this is to say that once we've introduced this margin of error, these are the plausible values for P. We don't know P exactly. We know P hat exactly. It's 0.37. We believe that P is somewhere between 34% and 40%. Now, in the example we just looked at, we were given the margin of error straight up. So we're going to start to look at something we can do mathematically when we're not given a margin of error. And it's all based on a sampling distribution. So we're looking at just this example using a mean, a sample mean x bar and a population mean mu to see how this works, and it works the same way for proportions as well. But if we look at this first graph, this is a sampling distribution for the mean x bar, assuming that mu is known, so that the population parameter is actually a known value. Recall that the 95% rule states that 95% of the values in this distribution, if the distribution is approximately bell-shaped, sit within 2 standard deviations of the mean. Well, in this example, since we're talking about a sampling distribution, the standard error is the same thing as the standard deviation of this distribution. So this first one tells us that there's a 95% chance that any value x bar is going to lie within 2 standard errors of the mean mu. We could mark an x bar on here. Let's say right here. We have a 95% chance of it falling between these two values, mu minus 2 times SE and mu plus 2 times SE. What we do in this second graph is we flip this around because we don't know mu. So in the second graph, we're assuming that mu is unknown, and all we can do is center the graph on our best estimate, which is x bar. So x bar certainly is known. This is a sample mean. This is something on which we have gathered data. Well, if that x bar was within 2 standard errors of mu with a 95% chance, then that suggests to us that mu is within 2 standard errors of x bar, but now we call it 95% confidence instead of a 95% chance. We used the language of chance in the first case because x bar is random. It's based on a random sample, and it's going to vary depending on how that sample is taken or depending on which sample you're looking at. Mu does not vary. Mu is an unknown constant. So all we can do is talk about how certain we are about our estimate of mu. We don't talk about mu using language of random chance and probability. So if we're 95%, we have a 95% chance in the first example, given a known value of mu, we have a 95% chance that x bar is in that interval. When we turn it around and look at it in the other direction, based on our value x bar, we now have 95% confidence that mu is in this interval. So the takeaway from this is that we have two endpoints of this interval. They are x bar minus 2 times the standard error and x bar plus 2 times the standard error. And that tells us that this is how we find a confidence interval, that these two bounds here create my confidence interval. And in fact, this is a 95% confidence interval because it's all based on the 95% rule. And that tells us also that the margin of error in this case looks like it is equal to 2 times the standard error, since that's the value that we added and subtracted in order to get from our estimate to the upper and lower bounds of our estimate for the parameter.